something that's really called Lenz's law, but Lenz's law is this idea of getting current to flow. So we're just going to throw out somebody's last name there. People do call it Lenz's law. Just FYI, if you're Googling it online or something like that, or asking the AI for help. Anyway, stepping back from the right-hand rules, things that are true. Current is moving charges. Oops, I'll use a pen that's not drying out. Moving charges. True, as a fact. Regardless of if you're talking about electron flow or conventional current flow, it's all about moving charges. Fact. Moving electrons really do cause magnetic fields. I know that we talk about conventional current flow, but conventional current flow is really a consequence of moving electrons. Okay, so they're doing this. And magnetic fields caused by current can interact with external magnetic fields. Okay. So now we're saying that magnetic fields caused by current in a wire, for example, are going to interact with external magnetic fields, and as a result, that causes a force. Right? So we're not explicitly stating this as a right-hand rule, we're just stating this as sort of a series of facts. And what we were saying just previously was kind of the answer to this question: can we turn cause and effect on its head? In other words, the outside magnetic field can induce magnetic fields around a wire. And I want to add something to the front end of the sentence. I don't usually add things to the end or to the beginning. I usually add to the end. But I should say changing. Changing those outside magnetic fields can induce magnetic fields around a wire. Changing the intensity or the orientation of the magnetic field around a current carrying wire is going to induce a magnetic field around that wire. And then as a consequence, we get something that a lot of people call the generator effect. And that generator effect is the act of using a magnetic field to cause current to flow as a result of pushing a conductor through a magnetic field. Now, I'm just kind of trying to be everyday and folksy about how I say this. When I say pushing a conductor through a magnetic field, I could push a magnetic field towards a conductor. Really what we're talking about is causing a magnetic field flux or a magnetic field change around that conductor, whether you're moving the wire itself or whether you're using the magnetic field and moving the magnetic field. Or in the case of an electromagnet, maybe you could jack up the current on the electromagnet while it's near a wire, and that would change the magnetic field around that wire. You guys kind of get what I'm saying? So when I say just push a wire through a magnetic field, there are a variety of ways to push a wire through a magnetic field, is all I'm trying to get at with that. I just don't want to write all those things down. I think you guys are clever enough to figure that out. Before we continue writing down this left-hand column, I want to take a look at the right-hand column. And the right-hand column was actually a series of pictures. And I want to make sure that we get this idea. So it's a little bit of a recap in a way, because we talked about it with solenoids before, but this diagram from a textbook is just a single loop. So in this diagram, I've got, it's hard to read maybe, this is a north and this is a south on a permanent magnet. And if we shove a north into a single loop of wire even, then that's going to cause current to flow one way around that loop. And it's actually going to set up an oppositional magnetic field. So that loop, actually, that single loop of wire has a north on one side of it, and it has a south on the other side of it. So if I reduce a solenoid down to like a one loop solenoid, it would be like that. But then if I take this magnet, maybe I should emphasize, in the first diagram, we're taking this magnet and shoving it up. In the second diagram, the action is that we're going to take that same magnet and yank it away. And so we have this north and this south now being pulled out of the single loop. And as a consequence, the south a south end is induced in the bottom of the loop saying, no, north, don't go away, and a north on the top. And that's going to induce the current, maybe I'll label up the current, to go a different direction around that one loop. And you notice the current's going one way in the first loop and going the other way in the other loop. And earlier I talked about an analog ammeter because in my imagination I was working towards this picture, okay, like just so that we could kind of have this idea. And I think at some point I thought that this illustration wasn't clear enough, so I said, well, in picture A, there's picture A and this is picture B. In picture A, we're pushing the magnet up, and in picture B, we're pulling the magnet down. Okay, so at some point I thought I had to make that picture more clear, but I don't know if it helps at all. All right, so down here we've got another illustration, again stolen from a different artist, but this artist says, what I want to think about is taking a single wire and pushing a single wire with a force. So there's my force. See, this is all three-dimensional, and we're pushing this wire through this magnetic field. Now, the reason I bring up this picture is because I think it helps us to engage with the right-hand rules a little bit. So let's think about this. If I push the wire this way, according to this artist, the current ends up going that way. See the vector? Now everybody immediately gets their right hands out, and I'll zoom out so that I can get this idea on camera. Obviously, I could go to the whiteboard in class, but look, here's my palm pushing in the direction of that force. You see what I'm talking about? And immediately you see my thumb coming out of the page, yeah? But you see this artist sent the current into the page. But what I said earlier was that the generator effect is kind of the opposite of what we've been talking about. The input now is the force. Previously, the output was the force. And so it turns out that the generator effect drives current not according to a right-hand rule, but according to a left-hand rule for straight conductors. Because it's the opposite. So there's an opposite-handedness to the rule. So in this case, hey, whip out your left hand. Hey, why not? If I push, I'm still looking at this picture number 1 here, if I push in the direction of my palm, then the current goes that way. Everybody okay with that? So this is our first left-hand rule, if you like. Everybody cool with this idea? You look at the next diagram, the person stopped pushing. If they stop pushing, we said this before, there's how much current? None. Zero current, yeah. Take a look at diagram number 3. Notice again that the force has been illustrated with this double bold arrow, and we're going to take that wire, and I whip out my left hand because now we're in the generator effect mode, and we're pushing that wire in the direction of my palm, and you notice that the artist has thrown in, I'll emphasize it, a capital I right there, going in that direction, kind of out of the page. Am I kind of selling this with pictures? All right, so right-hand rule would be for the motor principle. We called it that earlier. Left-hand rule is for this so-called generator effect. Okay, motor principle is a straight wire in a magnetic field experiencing a force as a consequence. The generator effect is a straight wire in a magnetic field where I apply a force and produce a current. Okay, different input, different output. We're actually just reversing the input and the output. Anyway, people use this word, EMF. Well, EMF is a short form. The idea is behind EMF, and they often will write it as like a cursive capital E, but EMF is electromotive force. Electromotive force is exactly what the compound word looks like. It's the force that moves an electrical thing in a certain direction. Okay, so we're talking about an electrical thing being like an electron. Okay, so inducing a current. So the direction in which the current is induced to move is induced to move through the conductor or maybe I should zoom back in again. Sorry for being so small. Nobody complained, but myself focused. The direction in which the current is induced to move through the conductor is dependent on which direction the wire is pushed. And I already said you don't literally have to push the wire. You could push a magnet closer to the wire. You could change the magnetic field strength near the wire. Okay, so when I say wire pushed through a field, that's what I'm also implying as a possibility. And then the electron force, let's just call it that in quotes, because it's the force experienced by the electrons, is called the electromotive force. Motivating an electric charge to move along with a force. EMF. And not even just as a side note, but as a takeaway in terms of figuring out what direction it is, we use the left-hand rule. And remember, it's not like it's a law of physics that it has to be your left hand. If you encounter a friend or a family member that somehow maneuvers their right hand to make an XYZ axis to make this happen, that's fine. It's just that it's the opposite of the motor principle. Okay, so if you have a family member that teaches you a fourth right hand rule, fine. Okay, I'm emphasizing that it's the opposite by using a left hand. That's all. That's why I'm using a left hand rule. And you'll find a lot of people do that just to emphasize that it's the opposite of the motor principle for this cross product. Oh, and I slipped and I used a math term because it really is the multiplication of two vectors producing a third perpendicular vector. And if we want to have a hand diagram, you can do this diagram for yourself if you want to. It depends on if you want to be like all artistic. Oh my gosh, I'm just going to make all my fingers the same length. I know that sounds like so mutant, but oh my gosh, this looks like so terrible. I should have practiced my right hand. Look at the size of that pinky. I'm sure that's like indicative of some genetic disorder. Anyway, if I want to label up which vectors are which, the palm is the direction of the force on the wire. The thumb is the direction of the current flowing through that wire as it's been induced. And then fingers shooting out the tops of this hand are the orientation of the magnetic field for this left-hand rule. Okay, for that left-hand rule. And then the direction of the induced current in a loop will set an opposing magnetic field to the external field. And we talked about that previously and how we could think that out using a solenoid. And with this idea of the solenoid, sometimes people say, well, that's kind of like an example of a piston style generator. And the most basic kind of oppositional AC generator we talked about was this idea of the solenoid with a magnet getting shoved in and out. And that's what I mean by the piston style generator. Also sort of illustrated at the top of the page as a single loop motor. Nobody does single loop. Single loop generator. Nobody does single loop generators though. They always have more and more coils to get more and more out of the action. Anyway, according to right hand rule number 2 for solenoids, the magnetic field of the solenoid will have a current that follows the direction of the fingers. So if I do decide to not just push straight wires through a magnetic field, but instead to have a solenoid like this and shove a north into it, then that action of shoving it in will produce an induced north and south in the solenoid to oppose the incoming permanent magnet coming in. And that means that I would have a right-hand rule for that solenoid, because the right-hand rule for solenoids has not gone away. Oh my goodness, another terrible hand drawing. So that this right hand is related to this solenoid. Thumb is the north, and the fingers are the current direction. So on my solenoid, the current would be flowing in this direction.